Okay, so let's dive right into this explainer, because today we are tackling what is honestly one of the most massive, still unresolved challenges in the world of autonomous machines. For years, AI has lived super comfortably behind our screens, right? Just answering our questions, generating images, maybe writing a bit of code. But right now, we're entering a whole new era. AI is literally stepping out of the digital realm and into the messy physical space around us. And that huge transition, well, it brings up a terrifyingly practical question that researchers are scrambling to answer.
And that question is, how on earth do you grade a robot's homework? Seriously, as these autonomous systems enter our real physical world, we have a really critical problem on our hands. How do we accurately judge if an AI's reasoning is actually physically possible? Just think about the stakes for a second. If a chatbot makes a reasoning error, you get a weird, hallucinated paragraph. It's annoying, sure, but totally harmless. But if a robotic arm makes a reasoning error in your kitchen, it shatters a plate. Or worse, if an autonomous car messes up its spatial reasoning, the consequences are literally life-altering. The margin for error is suddenly zero.
Section 1. The Physical AI Frontier.
So we are building these absolutely incredible physical AI systems right now. On one hand, we've got these highly articulated robot arms learning to navigate the super tight, cluttered complexities of human kitchens. And on the other, autonomous cars that are literally tasked with making split-second decisions on rainy, completely unpredictable streets. It's a massive leap from where we were just, a few years ago. We aren't just asking computers to process data anymore. We're asking machines to navigate a physical world full of friction, gravity, and honestly, complete unadulterated chaos.
And because of that chaos, physical AI has entirely different requirements than traditional AI, which just, categorizes flat images on the internet. Physical AI requires interpreting really complex, multi-view observations of 3D spaces in real time. It needs to deeply understand object affordances. Basically, that means knowing what an object can actually be used for in the real world. And crucially, this is the big one, it requires reasoning over causal dynamics, meaning it has to understand cause and effect. It needs to know that if you push a glass off a table, it's going to fall and shatter, not just magically float in midair.
Section 2. The Evaluation Gap.
So right as we're making these incredible leaps forward, we hit this major roadblock. We desperately need a way to evaluate if these new physical AI models are actually doing a good job before we just let them loose. But here's the catch. Our current AI judges, the massive models we use to grade other models, well, they grew up reading the internet. They're total masters of text, static images, basic Q&A. But they don't actually know what gravity feels like. A true physical AI judge has to assess causal validity, spatial constraints, and actual real-world physics, things those general models fundamentally lack.
Which leads to some completely absurd situations. Like, a standard AI judge might actually approve a robot's plan to push a tray into a closed oven, simply because the verb push makes grammatical sense next to the noun oven. It completely ignores the literal physical impossibility of pushing a solid object through a closed glass door. It just lacks true physics awareness. It acts as if the robot can just, ghost its hand through solid matter. Bottom line, we absolutely cannot rely on spell checkers to grade physics exams.
Section 3. Introducing PhiCritic.
To solve this absolutely critical safety gap, we need a totally new kind of judge. Enter PhysiCritic. Now, in technical terms, this is a multimodal critic model that's explicitly optimized for this exact problem. But in plain English, it's an AI supervisor that can process video, images, text, and is explicitly built to act as a rigorous physics professor for other robots. It evaluates a scenario, looks at a robot's proposed action, and decides if that action actually obeys the hard laws of physics and spatial reality.
Developed by researchers at NVIDIA and the University of Maryland, this is honestly the bridge we've been missing in robotics. It connects the abstract, kind of floaty world of language processing directly to the hard, unforgiving reality of the physical world. It is a massive step forward in making sure robots actually act safely and logically when they're interacting with our environment.
At its core, its whole job is to be the ultimate reality check. It evaluates other models' outputs to verify if our proposed plan makes sense. It checks if the reasoning is causally valid. It ensures the action is visually grounded, meaning it actually lines up with what the robot's cameras are seeing in that exact moment. And it makes sure the plan respects physical constraints, so you don't have an AI out there trying to force a square peg into a round hole or trying to walk straight through a brick wall.
Section 4. Self-referential training.
Okay, so how do you actually teach an AI the laws of physics so it can accurately grade others? Well, the researchers relied on this brilliant intuition. A strong physical critic should behave like an expert human judge. Before evaluating other models' responses, it should first solve the problem itself. Think of it exactly like a math teacher. A good math teacher has to solve a complex equation on scratch paper themselves before they're allowed to pick up a red pen and grade a student's test, right?
To create this expert teacher, they build a highly specialized two-stage training pipeline. Stage 1 is a physical skill warm-up. Basically, it's giving the model a crash course in basic physical reasoning using targeted question and answer pairs. Then comes Stage 2, the real secret sauce here, self-referential critic fine-tuning. In this stage, the model is strictly forced to predict the outcome of a physical action itself before it's even allowed to look at or grade any other AI's proposed answer.
To enforce this super strict rule, the researchers completely rewired how the AI is prompted. The system is rigorously commanded to first write out its own reasoning process and then generate its own answer totally independently. It uses that internal self-prediction as an anchor. Only after that internal monologue is completely finished and it has solved the physics problem on its own can it look at what the candidate robot wanted to do and give it a grade. It's a really clever way to create incredibly stable and grounded physical judgments.
And this brilliantly illustrates the result of that rigorous training. Imagine a robot tasked with cooking vegetables. Because PhysiCritic evaluates the raw visual scene first, it notices a really crucial detail. The oven door is already closed. So when it starts grading, it correctly rewards the AI candidate that decides it needs to press the start button. On the flip side, it actively penalizes the AI that blindly tries to push a tray further into a solid glass door. It actually caught the physical constraint.
Section 5. Results and future impact. So does this rigorous solve-it-first method actually work in practice? Well, let's look at the data. The researchers put PhysiCritic to the test on two distinct battlegrounds to see if it truly grasped physics. First, they tested it as a judge. Can it accurately grade the outputs of other models? And second, they tested it as a primary problem solver. Can it actually perform complex physical reasoning tasks on its own, completely without relying on another system? The benchmark results? Incredibly clear. PhyCritic achieves an overall score of 68.0, showcasing massive, double-digit performance gains over its competitors. It effortlessly outsmarts general-purpose models of similar sizes, leaving other systems far, far behind when it comes to understanding physical reality. It turns out, teaching a model to solve the physics problem first makes it a drastically better judge, like a real game-changer.
And perhaps the absolute best part is this fascinating spillover effect. By learning to rigorously critique physical actions, PhysiCritic actually becomes a better, active policy model itself. In plain terms, that just means it gets better at executing the physical tasks directly. Just like in real life, being an observant, rigorous teacher forces you to understand the material so well that you naturally become a much sharper practitioner yourself.
Now, to ensure these results aren't just some fluke in a sterile lab, the researchers built a massive new benchmark using incredibly diverse datasets. They pulled training and testing data from everywhere, ranging from human eye perspectives of daily chores to real-world footage of actual robotic failures and crashes. PhyCritic was put up against the messy, unpredictable reality of our world to ensure its judgments actually hold up when things go sideways. So as robots step into our physical world, who is watching their every move? Well, with PhyCritic, we finally have the specialized, physics-aware supervisor needed to ensure our autonomous future is safe, logical, and grounded in reality. The next time you see a robot navigating your grocery store or an autonomous car turning down your street, ask yourself who is watching their every move to ensure it actually makes sense. Now, we have a concrete answer. Thanks so much for joining me for this explainer, and definitely keep questioning the logic behind the technology around you.